Hello everyone. Today we're going to be covering 4.5 and A.6 on properties of rational functions and then solving rational equations. So let's go ahead and get into it. First, we're going to talk about our steps to graph a rational function. To graph a rational function, we are always going to start by graphing the numerator and the denominator. A rational function is a function where I have a polynomial in both the numerator and the denominator, and both of those may or may not be factorable. So I'm going to try to factor them as much as possible. Then I'm going to find the domain and determine if there are any vertical asymptotes or holes. The domain, since this is going to have a denominator, domain is going to happen when the denominator is not equal to 0. Next, we're going to find x or y intercepts, find any horizontal or oblique asymptotes, and then determine if the function intersects the horizontal asymptote or oblique asymptote by setting the function equal to that value and solving for x. And then we can sketch the graph. We can always use our calculator to help us sketch our graph. Okay. At any point during this video, if you need to, obviously you can pause to finish copying any notes. We're just going to keep going. Okay. First is how do we find horizontal asymptotes? So we have this rational function of this form f of x equals a times x to the n over b times x to the m. There is a horizontal asymptote at y equals 0 if the degree of the numerator is less than the degree of the denominator. There's a horizontal asymptote at a over b, so the ratio of the leading coefficients, if the degrees are equal. And then there's no horizontal asymptote, but there is an oblique asymptote if the degree of the numerator is bigger than the degree of the denominator. So we use these rules to determine where the horizontal asymptote is. Please make sure you have these copied down in your notes. Okay. Next, we just have this table that we can use to kind of help us as we're working through identifying properties of a rational function. First, finding vertical asymptotes. These are the values of x that make the denominator equal 0. So we find these first by setting the denominator equal to 0 and just solving for x. A hole in a function is going to be a value of x that makes the denominator equal 0, but that I could factor out. So when I factor the numerator and denominator, if they have any common factors, I'm going to cancel those out. So a hole in the graph is something that was able to be canceled out. We use those same rules that were on the previous page for horizontal asymptotes. And then we can find oblique asymptotes if necessary. So if there's no horizontal asymptotes, by using long division to divide the numerator by the denominator. And we talked a little bit about long division in our last unit when we were talking about polynomials. Okay, so again, pause if you need to copy the table. We're going to keep going to our first example. Is 4x plus 1 over 2x plus 1. And when we're working with rational functions, the first thing we always want to do is factor the numerator and denominator completely if possible. Here, 4x plus 1 is just a linear expression. There's no common factors, no GCF that I can factor out. So that's fully factored. 2x plus 1 is fully factored as well. So first thing we can do is look for our asymptotes. So nothing cancels out. That means there's no holes in the graph because nothing cancels. So that's one feature that we can go ahead and say. So then going into vertical asymptotes, to find our vertical asymptotes, we set the denominator equal to 0. So that's 2x plus 1. And we solve for x. So we subtract over the 1, 2x equals negative 1, and then we divide by 2. So I'm going to have a vertical asymptote here at x equals negative 1/2. Okay, let's then next find our horizontal asymptote. And we get the horizontal asymptote by comparing the degree of the numerator to the degree of the denominator. Both of these are just linear, right? So the degree, there's that invisible power of 1 on the x. So that means the degree of the numerator is equal to the degree of the denominator. And that means there's a horizontal asymptote at y equals 0. Okay, so we have a few features. We have that there's no holes in the graph, there's a vertical asymptote, there's a horizontal asymptote. Next, let's look for the intercepts. So to find the y-intercept in our graph, we are going to set x equals to 0 and solve. So we do 4 times 0 plus 1 over 2 times 0 plus 1. So the zeros cancel. We have 1 over 1 equals 1. So there's a y-intercept in my graph at 0, 1. To find the x-intercept, we can just set the numerator equal to 0. So if we set the whole function equal to 0, that's fine, but our denominator is going to end up canceling out when we divide it or multiply it over. So we can save ourselves some time to find x-intercepts in rational functions by just setting the numerator equal to 0. So we would do 4x plus 1 is equal to 0. I subtract over the 1, and I divide by 4. So I have an x-intercept at negative 1/4 or negative 1/4, 0. Okay. We could continue here to graph by plugging in our function into our graphing calculator, looking at our table to identify some key points, and then doing our sketch. Okay. Example 2 is really similar. Instead of just 4x plus 1 over 2x plus 1, we have 4x squared plus x over 2x squared plus x. So we have this extra factor of x. And again, our first step when we're kind of evaluating and looking at features of these functions is to factor. So we want to fully factor the numerator and denominator. In this case, they both have a GCF, We have x squared and x, so we can always factor out the lowest power of our variable. So we pull the x out front and then divide through. 4x squared divided by x is 4x. X divided by x is 1. Then 2x squared plus x also has a GCF of x. 2x squared divided by x is 2x, and then x divided by x is again 1. So this time these have this common factor of x, and any common factor that's in both the numerator and the denominator, I can just cancel out. So I cancel that function or that factor of x out, but remember, any factor that cancels out is going to represent a hole in my graph. So here there's a hole where that factor x equals 0. And now I'm left with that function that I had on the previous page. So this is going to have all the same features as that last graph, with the one difference of a hole at x equals 0. So that's a gap in the domain of the function. Okay, we can put this graph again into our graphing calculators, or this function into our graphing calculators. When you plug it into your calculator, just make sure we put parentheses around the numerator and denominator. And our graphing calculator isn't going to put the asymptotes on the graph. That's something that we have to do, which is why we get the asymptotes to start. It's also not going to put the hole in the graph. That's also something we have to do, which again, that's why we look for those features first, and then we just use the graph to help us do our sketch. All right, let's look at another one. For example 3, we have f of x equals x plus 1 squared times x minus 3, and then x plus 3 squared times x minus 2. So this is fully factored, right? Everything is factored completely. There's no common factors though, right? So there's nothing that I can actually cancel out, which again means there's no holes in the graph because nothing cancels. So that means we can go ahead and look for vertical asymptotes by setting the denominator equal to 0. So if our factors are equal to 0, we separate and solve. So either x plus 3 squared equals 0, or x minus 2 equals 0. If we take the square root, we can just cancel the square, since the square root of 0 is still just 0, and then subtract over the 3. So I have two vertical asymptotes this time, one at x equals -3, and one at x equals +2. So if we were going to do a little sketch of a graph, we'd have -1, 2, 3. There would be a vertical asymptote right there. And then +1, 2, there's a vertical asymptote here. Okay. Next, let's look for our horizontal asymptotes. And horizontal asymptotes we get by comparing the degree of the numerator and denominator. Here I have in factored form. So in factored form, I just multiply out my factors. So I have an x squared and an x to the first, which means the degree would equal 3. And again, I have an x squared and a power to the first, so the degree is equal to 3. I just add up the powers on all of my factors. So degrees are equal again, which means I have a horizontal asymptote at y equals 0. Y equals 0 is the x-axis, so that is right on top of the x-axis. And the horizontal asymptote is telling me the end behavior of my function. So it's just telling me that as this function goes out in both directions, it's going to be getting really, really close to 0 in both directions. Okay. We can also find our x and y intercepts again. We find our y-intercept by setting x equal to 0. So I would have 0 plus 1 squared times 0 minus 3 over 0 plus 3 squared times 0 minus 2. So that's 1 squared is just 1. 0 minus 3 is negative 3. This would be 3 squared is 9. 0 minus 2 is negative 2. It's negative 3 over negative 18 is 1/6. Okay. Then to find our x-intercept, we set just the numerator again equal to 0. So that's x plus 1 squared times x minus 3 equals 0. If x plus 1 squared equals 0, that's just x plus 1 equals 0. And then x minus 3 equals 0. So we get x equals negative 1 or x equals positive 3. So those would be my two x-intercepts. So there would be one right here and then one at positive 3. Okay, and then finally, again, we can plug into our calculator. We can check everything that we've looked at so far, our asymptotes, our, oh my gosh, you know what I just realized is I've been using the wrong rule. The degrees are equal, and I've been saying that means that y equals 0 is the horizontal asymptote, and that's not true, right? When the degrees are equal, the horizontal asymptote is the ratio of the leading coefficients. So this would be, instead of a degree, or instead of a horizontal asymptote at y equals 0 for this first example, we should have had a horizontal asymptote at, sorry about that, guys. So we should have had a horizontal asymptote at y equals 4 over 2. The numbers in front over each other. 4 over 2 is equal to 2. So we have a horizontal asymptote at y equals 2. So we have a horizontal asymptote at y equals 0 only when the degree of the numerator is less than the degree of the denominator. And then same thing for this example. The degrees are equal. So we should actually have a horizontal asymptote at the ratio of the leading coefficients. So that is y equals In this case, there's nothing in front of our two x's, so that's 1 over 1. My horizontal asymptote is at y equals 1. Everything else is exactly the same. I just mixed up my rules, which is why, again, it's important to have them written down in your notes so that you can reference them as you go through and do the practice. Okay, and so we sketch our graph, again, using our graphing calculator, but again, your graphing calculator is not going to plot your asymptotes, so you need to know how to find those algebraically first. And then this graph didn't have any holes, but we would also want to make sure we knew how to find those algebraically first. All right, next example is x squared minus x plus 4 divided by 2x plus 2. And the first thing I'm going to do is factor the numerator and denominator. For the numerator, x squared minus x plus 4, I'm going to look for two factors of 4 that add to -1. And I consider this 4 has factors of 2 and 2 or 4 and 1. There is no way to make that equal -1. So that's just not possible. In the denominator, I do have a common factor of 2. So I could factor the denominator. Just by factoring out the GCF of 2. Okay, and then I can start to look for my features. So in this case, there's not a hole because there's no factors that will cancel out. So no hole, I can start to then look for a vertical asymptote. And my vertical asymptote is where the denominator equals 0. I realize I factored this. This is x plus 1. I didn't divide it all the way out. This is 2 times x plus 1. The 2 divides by 0, so it just cancels. And then if x plus 1 equals 0, x equals -1. Okay. So there's my vertical asymptote. This time the degrees, if we start to look for our horizontal asymptote, we look at the degree of the numerator is 2. The degree of the denominator equals 1. So going all the way back to our rules for horizontal asymptote, the degree of the numerator is bigger than the degree of the denominator, we know that there's no horizontal asymptote. So n is bigger than m, no horizontal asymptote. When there's no horizontal asymptote, I take the function and I do long division to find an oblique asymptote. So I look for my oblique asymptote by doing long division. I would put the 2x plus 2 on the outside, and I'm dividing this into x squared minus x plus 4. So remember, to do log division, I divide, multiply, subtract. So I divide my first terms. X squared divided by 2x is x over 2. Then I multiply. X over 2 times 2x is x squared. X over 2 times 2 is x. Then I subtract. X squared minus x is cancels. Negative x minus x is negative 2x. And then I drop down my last term. Negative 2x, I repeat the process, so negative 2x divided by 2x is negative 1. Negative 1 times 2x is negative 2x. Negative 1 times 2 is negative 1. Not negative 1, negative 2. Then I subtract. Negative 2x minus negative 2x cancels. 4 minus negative 2 is 6. 6 doesn't have an x. This is our remainder. When I'm looking for my oblique asymptote, I don't need to worry about the remainder. So my oblique asymptote happens here at x over 2 minus 1. Okay. And we can look for intercepts. I'm not going to repeat that process because we've done it so much already. And then we can look at the sketch of our graph, where we know we had that vertical asymptote at negative 1. And then we have our oblique asymptote as well. Okay. So in our next example, we want to identify some features of the function from its graph. So let's look at this graph. We first want to identify the vertical asymptotes. Here we have vertical asymptotes where kind of my function is following out. So here I'd have a vertical asymptote right here where my function's following that line up and down. It looks like I also have a vertical asymptote right here where the function is following the graph down in both directions. So my vertical asymptotes were at x equals negative 1 and y equals 2. The horizontal asymptote could be more than 1 as well, or no, we can't. Horizontal asymptote, we're only going to have 1. In this case, this is describing the end behavior, so what's happening at the end. Both ends of my graph are approaching the x-axis. So that means the horizontal asymptote here is at y equals 0. Then identifying my x-intercepts, I have one x-intercept right here at negative 2, one right here at positive 3. My y-intercept is down here at negative 2. For my domain, I'm always skipping the vertical asymptotes in my domain. So my domain goes from negative infinity up to the first vertical asymptote at negative 1. It skips that and goes from negative 1 to the next vertical asymptote at 2. And it skips that and goes from 2 all the way to infinity. And lastly, for the range, this function crosses the horizontal asymptote. So there's no gap in the range. So this is all real numbers. And that's all of our features. Okay, that brings us into A.6, which is solving rational equations. When we solve rational equations, we always want to start by checking the domain. So we want to make sure that our solutions are in the domain and they're not one of those values that's excluded that would make the denominator equal to 0. Right? So sometimes we'll have to throw out a solution if it's extraneous, if it causes the denominator to equal 0. Okay, so our first one is 3/5 x plus 2 over 15. This time there's no x in the denominator. We just have these fractions. So there's no domain restrictions. To get rid of our fractions, we're always going to multiply by the least common denominator. Here, the least common denominator for 5 and 15. This is kind of thinking of if I were going to add the fractions together, what would I want my common denominator to be? And that would be 15. So to get rid of the fractions, I can multiply everything in the function by 15. You can use your calculator if you need to help you simplify. 15 times 3/5, I would do 5. 15 divided by 5 is 3, times 3 is 9. And 2 over 15 divided by 15 is just 2. The 15s cancel. 1 times 15 is 15. Then this just becomes a pretty straightforward linear equation. I would subtract the 2, so 9x equals 13, and then divide the 9. And that's it. There is no domain restrictions, so we don't have to worry about throwing anything out. Okay, next I have x plus 12 over x equals 7. In this case, there is this time an x in the denominator. So I find my domain restriction. And the restriction happens when x equals 0, when the denominator equals 0, right? So I would say it's actually not allowed to happen. Remember, whole numbers have a denominator of 1. So our least common denominator here is just x, the only thing in the denominator. So I multiply through by that. X times x is x squared. 12 over x times x is just 12. 7 times x is 7x. I now have a quadratic equation, so I'm going to subtract 7x over to get this set equal to 0. And then I can either graph, factor, or use the quadratic formula to solve. Looking for two numbers to factor, two numbers that multiply to 12 and add to -7. That would be -4 and -3. So we have x minus 4, x minus 3, If x minus 4 equals 0, x equals positive 4. If x minus 3 equals 0, x equals positive 3. Neither of those are my restriction, so both of those are solutions. Oops. All right, next I have a little bit more complicated one. I have x minus 3x and then x times x minus 3 in my denominators. So I set my least common denominator equal to 0 first to find domain restrictions. This time my least common denominator is x times x minus 3, right? Because this is x minus 3, this is x. This is just putting both of those together. So just like if these were numbers, right? If this was like 2, 5, and 10, my least common denominator would be 2 times 5, which would be 10. So I set this, I say, actually, this can't equal 0. If x equals 0, that means x can't equal 0. X minus 3 can't equal 0. That means x can't equal positive 3. Okay, then I switch over and I start to solve by first, I want to get rid of the fraction. So I'm going to multiply everything in the equation by x times x minus 3. The common factors are going to cancel, so x minus 3 will cancel. And this is 4x minus 8 times x. It's 4x squared minus 8x. Here the x will cancel. This is then 3 times x minus 3 would be 3x minus 9. And then here both factors cancel, so this is just equal to negative 3. Okay, so now I'm going to combine my like terms and add my 3 over to get this set equal to 0. This would be minus 5x. Negative 9 plus 3 is negative 6. This time if I wanted to factor to solve, a is not 1. So you can use whatever your preferred method is to factor when a is not 1. I like to use a big X on my page and multiply a times c. So 4 times negative 6 is negative 24. And then we have negative 5. But when a is not 1, I also need to reduce my factors. So I usually put that in a T-chart with ax at the top. And then I think through negative 24. So 24 has factors of 1 and 24, 2 and 12, 3 and 8. I make 8 negative, negative 8 and 3 will add to negative 5. So I put those in my T-chart. I can then reduce my T-chart if possible. 4 and negative 8 have a common factor of 4, so I can divide that out. 4 and 3 don't have any common factors. So my factors are x minus 2 and then 4x plus 3. If x minus 2 equals 0, x equals 2. If 4x plus 3 equals 0, x equals negative 4/3 or negative 3/4. Again, neither of those are in my restriction. So this would be my final answer. Right, that's it. Thanks for watching.